Hello, everyone. Welcome to the Community Energy Systems from the Full Value Chain Perspective. This workshop has been organized by Creators H2020 project. Creators is a project Creators stands for Creating Community Energy System, and the main objective of Creators is to enable community energy systems across Europe. So the aim of this workshop is to address community energy systems from the full value chain perspective. We have been working in Creators for over a year now, and we already have some knowledge that we want to share. Our consortium is really well positioned, and we are present in different parts of the value chain to create and to promote community energy systems, and that's what this workshop is about. So our intention is to share the perspective from AECOO companies, including architecture, engineering, construction, from the business perspective, from the operator owners, and from technology enables. So I'll be the moderator of the session. My name is Blanca Barrios. I work at R2M Solution. I'm the responsible of communication and dissemination of Creators project. And together with many partners involved in the projects, we will be sharing insights about community energy systems. So this is the overall agenda of the workshop. We will have two sessions, the plenary and the technical sessions. And in between, we will do a little break. So in the plenary session, we have our partner COMSA, our partner Energy Pro, our partner Joseph Stefan Institute, together represented with Acrony, Bax & Company, and Cordell. And in our technical session, we have AECOO, Typhoon Hill. So in the plenary session, we will have an introduction to the Creators project made by Hill van der Broek. We will address community energy systems from construction companies with the participation from Cordell and COMSA. We will address the business perspective with the participation from Bax & Company and EP Group, and the owner-operator perspective from the Institute Joseph Stefan. In our technical session, we will have the contribution of our partner AECOO and Typhoon Hill. So first of all, I would like to introduce you to our speakers. First, we have Hill, representing Cordell. We have Marco Rodriguez, representing COMSA. We have Julia Rinaldi, representing Bax & Company. We have Armin Meyer, representing EP Group. We have Boris Suchik, representing Institute Joseph Stefan. We have Igor Kovacevic, representing AECOO. Ivan Todorovic, representing the collaboration between Typhoon Hill and the University of Novi Sad. And we have Alexander Kavic from Typhoon Hill. So now I would like to leave the floor to Dr. Hill van den Broek, that is representing Cordell, that are also the coordinators of the project. So please, Hill, if you can.
Thank you, Blanca. I'm gonna try and take over the presentation screen. So let me know whether that works. Seems like it does.
Yes.
Okay. Perfect. So also from my side, and especially from Cordell as a Belgian company, I would like to also invite you to this afternoon workshop at Sustainable Places. Thanks first of all, Blanca, for the kind and nice introduction, and also for moderating this session. Bringing all those speakers together isn't always that easy, I recognize, so thanks for that. That being said, my goal for today with this presentation is to get you as an audience up to speed with the Creators project. We have brought together a quite unique consortium of very driven people that you will all meet this afternoon. And actually, we are all set to enable local initiators to create and operate local energy communities by supporting technical, financial, and social processes. That's in one sentence actually what the Creators Project as such is about. So we find therein the concept of local energy communities, which is hot and trending nowadays because of the advent of more and more distributed energy resources that actually enable us to build those communities where generation assets are combined with loads and distributed storage. But actually, we took on this challenge of completing Creators, starting from a few challenges that we all as Consortium perceived while trying to realize this model and put it into practice as companies. So the main challenge that we're addressing in Creators, actually, we recognize that there are already quite a lot of community energy systems out there, field trials, pilot installations, etc. And there is certainly a trend towards more of these, but today we are still in an experimental phase there. It are still typically government-supported projects that we're talking about. It are still projects where very few items are effectively being standardized. So there's still a lot to be investigated in order to put this into a more scalable model. So currently our estimates indicate that we reach about 0.01% of the current energy market with those pilots, with about less than typically 100 members typically. And also what's frequently the case is that those energy communities, although we talk about energy, actually we'll only talk typically about one energy vector at a time. We talk either about electricity, like in microgrids, for instance, or we talk either about heat networks, district heating networks, but combining them all together and really talking about an energy community as such is only in a number of limited cases applicable. And then, as I already put forward, the main issue we perceived as a consortium is that at the technical level, but as well on the business level, as well as the social processes, to get it through an energy community, there's actually very limited standardization. Those processes, when you start from it, everybody has his own approach, needs to figure out his own approach. How are you going to invite stakeholders to participate in such an energy community? How are you going to prove that participating in such an energy community is of actual value to them? And then when it finally comes down to realizing that energy community, how are you going to standardize on the technical aspects? So how are you effectively going to standardize on equipment, making sure everything is interoperable with one another? And as well on the legal elements, what type of standard contract should be put in place such that you don't need to have like all these negotiation processes that are lengthy and time consuming with each and every stakeholder in the game. And finally, when you enter into operating that energy community, how are you going to make sure that those participants remain engaged, that are incentivized, and how are you going to share those revenues? There are a high number of questions involved when realizing this, and those are the questions that we are addressing within Creators. And we are Creators. We are really a very driven consortium of industry leaders currently. So to briefly introduce you to all of them, I'll start with Typhoon Hill in this case. Alexander is also in the call today and will present more about that later on. But actually Typhoon Hill, together with the company AECOO, here on the right hand side of the slide, and Igor of AECOO is also present in the call today. those two companies actually, they cover the simulation and emulation part of the project. So they lead that activity because, of course, an important aspect in getting these local energies communities up and running is getting it up to the stage that you can really evaluate what are the quantitative benefits of building such a community, and eventually down the line, also how you're going to operate those energy communities. So there's a lot of modeling and simulation involved, both in real time as well as upfront. Then we have, on the more legal business models, financial aspects, we have Bax & Company together with Energy Pro as well as R2M Solutions taking on that part. So they focus more on those aspects within creators.
Just the caveat to say, Energy Pro has been rebranded to EP Group, so the two are the same. You will see them, but Energy Pro is EP Group and vice versa, essentially. So we're just trying to confuse you, keep you on your toes.
well, welcome EP Group then to the consortium as well. So luckily the faces remain the same. And then actually there are a lot of players I haven't talked about yet, like Acroni, Joseph Stefan Institute. So we have Boris on the call today presenting you their activities. And actually what all these companies have in common is effectively that they bring a pilot site to the creators project. Because within creators we go beyond just the study work, we go towards realization and implementation in a number of pilots that I will tell you more about in a minute. So the creators' objectives, first of all, realize a high-resolution simulation and emulation engine for the scoping phase. So that's Typhoon Hill and AECOO that are leading these activities. Therefrom, digital twins are being distilled for stress testing during the design phase. Alongside, we develop the business and financial models for those local integrators. And eventually, when those local energy communities are up and running, we will also come up with an automated trading platform to maximize the value in the operational phases. And all these four aspects are being demonstrated and validated at the 4 Tier 1 pilot sites. So those are the main pilot sites where we go all the way up to demonstration. And alongside, we have 5 follower sites in the slipstream that actually go up to the level of feasibility analysis, and some of them already also communicated their intent towards also implementation, because business cases prove to be valuable and viable. Here are all those pilot sites in a nutshell. So we have those Tier 1 pilot sites. We have, first of all, Acroni, located in Slovenia, major steel producer that, of course, needs to be very careful about managing their energy demand. We have Cordeel in Belgium, so that's a company I'm presenting today. So Cordeel is a construction company located in Temse, Belgium. Then we have the Port of Barcelona in Spain, that within the port they are aiming to integrate a variety of renewable energy sources, battery storage, EV charging, and also incorporating an ice factory in there because of its flexibility potential. And number 4 in line is Tartu, located in Estonia, having a high number of similar apartment blocks that also are being equipped with more and more renewable power on their rooftops, but also face a larger demand of charging infrastructure. What all these pilots actually share in common is that we're always talking about a combination of, first of all, replicability. So these sites are in fact a model for other sites that are very similar or with very similar characteristics. And secondly, especially for the first 3, we always have a cluster of industrial buildings and facilities, neighboring a number of residential facilities, apartment buildings, houses, where actually the trading between those two different load assets provides flexibility to the overall system and provides you, for instance, in the case of the Cordeel site in Temse, we will be able to use on-site generated PV generation to power the residential neighborhoods in times where there's actually low electrical demand on the industrial side, and vice versa. And then we have our Tier 2 pilot sites. We have 5 of them in total. One is an island, is Guadeloupe in France, where we have a landfill site located near a close, near a city that's nearby, so where they're considering to using their excess generation to power that city, as well as using the biogas that on these landfill sites is being generated. A similar pilot site we have in Kostinbrod in Bulgaria. Then we have Voorhout, the Netherlands, and a residential community. And we have the BTC shopping mall in Slovenia, also a major shopping center in the neighborhood there. Then we have Castilla y León in Spain, another industrial site that is completing the Tier 1 and Tier 2 pilots. Then, last but not least, are Tier 3 pilot sites. Those are the ones that we have not yet identified at this moment in time. We are more and more getting an idea about which ones will be eventually the Tier 3 pilot sites, but there our idea is that alongside the project we will engage those to further replicate the results developed in creators. After this introduction of creators, I'd like to share some more insights from the Cordeel pilot sites. And actually for the people that don't know Cordeel, as a brief introduction, actually Cordeel in Belgium is one of the largest construction companies in the country that are also having activities in the Netherlands, in Germany, in France, Bulgaria, etc. We're in total with 1,600 employees, generating an annual revenue of about 700 to 800 million euros. And Cordeel is a group, so we do not only cover construction activities, but we also conduct activities in like system integration, building operation, and maintenance services. That's then conducted by Intech company that's also taking part in the creators project. And this picture is actually the picture of our Tier 1 pilot sites in here. That's also then in the creators project. And it's effectively, I would say, or we call it internally, our playgrounds. So it offers us the opportunity to test technologies at scale before we replicate them with our customers. We have 2 MW of PV power, for instance, installed, and planning for many more energy assets in the upcoming years. And I'll show you some of them later. This is the headquarter building of Cordeel, located next to the River Scheldt, above a former dry dock where ships were being maintained and constructed in the past. We had the pleasure to have our General Assembly early next week there. And actually this building, because of its recent construction date, is also state-of-the-art in terms of its energy consumption profile and its capabilities to control the energy flows in there. For instance, meeting room reservations are being taken into account in controlling the indoor temperature at a comfort level to make sure that no heat or no cooling is being wasted in there when it's not required. Besides, of course, that this building also features some geothermal heat pump in there to also generate the heat and cooling in the most efficient manner. From a bird's eye perspective, the Cordeel site, so here's the headquarter I've been referring to in the last slide. And actually, this is the entire Cordeel site as such, with the dry dock and several production facilities that are all supporting the construction pipeline of Cordeel. We have wood joinery, we have prefab concrete production, metal welding and processing, and so further. But actually, Cordeel, of course, although it spans a large area in the city of Temse, we also have some interesting neighbors that we're willing to involve into this project. But first, let me show you already some of the energy assets that we have deployed in the past couple of years. First of all, is we're prototyping and testing here floating solar PV panels in the dry dock. Next, within the dry dock, because we have the river Scheldt nearby, which is running all the way to Antwerp, actually we have the capability here to also generate energy from actually the tides that happen. So we can generate tidal energy by opening those gates when water is high, and vice versa when the water is low, empty our reservoir again and generate electricity that way. Besides also having some limited storage capability by pumping water back and forth. More hydro energy on site that we harvest is by means of our energy hill. That's currently in the planning phase. So that's we use there the natural height difference that we have to cover about a volume of 10,000 cubic meters water volume, spending about 1 megawatt hour of electrical storage capacity. And then finally, also at the level of hydrogen, we have alongside, of course, obviously regular EV chargers, we also have some refueling station for hydrogen energy that has been installed early this year. So we're trying to experiment with all these energy vectors on site to gain experience with them from technical, operational, and also business level perspective. So most of these assets already covered. The ones I highlighted are mainly let's say the more extraordinary assets that you do not frequently encounter, like an energy hill to pump up water. It's of course not everywhere applicable. But I'd like to stress here also that we have two megawatts of solar PV generation. We have about 50 EV chargers on site. We have our heat pump powering the main headquarters as well as the hydrogen. And then these are the icons depicting the hydro energy pumping system. Throughout the years, we set ourselves a target to increase our self-consumption ratio of PV generation. Currently, we are at 68%, while our target initially was 65%, but we have adjusted that now up to 80%. Of course, our main and central goal is to lower the carbon footprint of the site as such, where we achieve currently about 23.5% of emission reductions. And of course, this also has an economic benefit in terms of lowering our energy costs. So we have the Cordeel site, and we also have our neighbors, our neighboring business park, where we have several types of companies, warehouses, as well as metal processing, as well as office buildings. So all those differences in load and generation profiles provide an incentive to interconnect them and exchange energy. And then in the upper right corner, we also have a residential cluster of apartment buildings that we can interconnect with the entire industrial site. So this is in a nutshell what I already presented. About something to highlight here is, why do we propose a local energy community here? That's because we observe that there's a significant mismatch between our on-site solar generation, especially in summertime, and the electricity consumption at that point in time, in weekends, but also during holiday periods where the entire site is being shut down, basically. So, and that way we can use that electricity in the local apartment residences, as well as power the neighbors that continue working during those periods of time, as well as basically making and prepping that local energy community to also aggregate the flexibility reserves we have on site and provide those services to the higher level grid in the system to help achieve the overall balance. And then one of the outcomes in the Creators project, one of the things that we started developing and are further developing throughout the project is our Empower gateway, which is actually a development that we started to make sure that in a uniform manner we can aggregate all those devices, interconnect them, and connect them to the energy management system of AECOO without the energy management system provider needing to worry about what were the latest settings and parameters of all these devices. So we're trying to make that interface as easy as possible, as accessible as possible, alongside having a level of redundancy in the system that in case a cloud connection would fail, that we still have some local control in place that makes sure that the system continues operating. Likely not in the most optimal manner as the cloud energy management system provider would provide you with, but still it will work and the lights remain on. So that's in a nutshell what we have been doing in the past year, and also about the Creators project in general, what we're aiming towards. And with that being said, I leave the floor to all the colleagues who will share some more interesting insights of the project with all of you. Thanks for your attention.
Thank you very much, Giel, for your contributions. As you can see, Cordel is a really important company in construction in Belgium, and the pilot site located at Cordel facilities is very interesting, and it combines a lot of energy assets. So we have a lot of work to do with Creators project to try to test our technology to see how will our energy community will work there. Thank you very much, Giel. And now I would like to leave the floor to our next speaker, Marco Rodriguez.
Hi, I'm going to share my screen. Just 1 second. Hi, thank you so much, Blanca and Giel, for the introduction and the moderating session. My name is Marco Rodriguez. I'm a project development engineer at Comsa Renovables, one of the key partners of this Creators project. Today I'm going to speak more about a general topic that also will be involved in most of the pilot sites of the Creators project. The topic is stationary energy storage systems as a key enabler technology for self-consumption in local energy communities. So the agenda for my presentation is, well, first of all, a brief description of what is Comsa Renovables as a holding section or as a holding company from Comsa Corporation Group as a construction company. The general view from a global building sector, also the self-consumption solar PV scenario in Spain, and generally speaking, the community energy systems or local energy communities concept in general. And then the application of these technologies into the tertiary building and industrial sector as well. And finally, another interesting topic that it's very related to this solution is the second life batteries as SESS applications for self-consumption, right? And then some future insights related to this application into the Creators Tier 1 and Tier 2 pilots. What is Comsa Renovables? Comsa Renovables, as I was telling, it's a holding from the Comsa Corporation Group. So basically, we are headquartered in Barcelona, Spain, and we are involved in the project promotion and development of mostly renewable energy projects as PV solar systems, wind power plants, efficient building or building management as well. But then we also promote different risk management studies, sustainability practices studies as well into the building, tertiary building sector and industrial facilities as our main core business. In terms of construction tasks, we develop also the construction project management, the asset engineering and project finances. Finally, as well, we develop the operation and maintenance of these assets, buildings, industrial parks as well. And then general services follow up, operational maintenance, asset control, and facility management in general. Well, a general view from the global building sector, just to introduce the topic more. Right now, or nowadays, after one report published by the International Agency of Energy, the CO2 emissions report says that 4.8% of the CO2 emissions growth after the pandemic lockdown that we had last year, but this year growth 4.8%. Then the 40% of the global energy consumption comes from the building sector in general. And then 36% of the total CO2 emissions are produced in the building sector, but produced in the European Union. So this is one of the sectors that we need to abate somehow in order to reduce the GHG emissions in conjunction with some energy route maps, public-private alliances as well in countries, and a proper mentality change in societies. And with this also the implementation of new green tech to accelerate the energy transition as well, we will manage to control these CO2 emissions and to reduce it as well. Speaking more about the Spanish self-consumption scenario, as we are a company headquartered in Spain, we're looking through the scenario of PV consumption, self-consumption, and the application of these scenarios in the Creators project as well. So here we have the scenario of the new installations for self-consumption PV in Spain. For the year 2020 or last year, we had 596 megawatts of PV capacity installed, compared with the 2014-22 only megawatts. So it has been a 1.5 gigawatt cumulative PV capacity installed during the last 6-7 years. So that must be that has been an interesting number to take into account. Another important data, it's the scenario related per sector or by sector in Spain that we have here in the last year. Residential sector accounts 130 megawatts, commercial sector accounts 137 megawatts, and finally the industrial sector, one of the most electro-intensive sectors, accounts 334 megawatts. So why are we focusing on this or on the Spanish scenario as well? Because the Creators project has 2 pilot sites in which COMSA is involved, and both of them are in Spain. One of these pilot sites is located in Castilla y León, the 6th community or autonomous community that has 844 megawatts of installed capacity for self-consumption as well. And then Catalonia, that we have another pilot site working on the Creators. It has 280 megawatts installed right now. So that's why we're focusing on these 2 autonomous communities at this moment, in which we want to develop local energy communities. In the case of Castilla y León, in an industrial park, and in the case of Catalonia, at the port of Barcelona. So getting involved into the topic, this is a brief introduction of what it is, a community energy storage system. So basically, this is a scheme in which we can interconnect all citizens, SMEs, and other participants in a decentralized energy scheme, and enhancing the figure of the prosumers, right? So we will gather investors, associations, prosumers, suppliers, local authorities that will want to participate and develop these new technologies and deploy them in other pilot sites, taking as reference the pilot sites of the Creators project. So basically, this is a diagram on how a local energy community will work, in which we have different multi-users and multi-vectors, right? So we have here the CES, or the Community Energy Systems prosumers, that will be the industries, will be the households, or the citizens or common participants that can have an installation facility to be interconnected with the local energy community. Then we have the asset owners, or the enablers and aggregators that will be the ones that will facilitate the development of these local energy communities through the implementation and operation of them. Then the suppliers and retailers that will also buy and sell electricity through the energy community as well. Then the network operators, market regulators, and finally the balanced responsible parties that will act as well as aggregators, in which they can provide ancillary services, or also continuous power balancing in demand and supply of this local energy community. Some of the applications of the local energy communities in the tertiary building and industrial sector. COMSA Corporación, as a construction company, it's focused in these sectors mostly, and here we can describe an interesting solution that can be applied in the project as well. So the deployment, or the enhancement of the GEVs, or the grid efficient buildings, the implementation of this solution, or of this type of buildings, into the, let's say, commercial and industrial sector as well, will adapt the new technologies and accelerate also the green electrification for the customers that will participate in these CES schemes, right? The assets to deploy for these solutions are mostly PV solar systems, or like BIPVs, or building integrated solar systems on the buildings, as well as the building energy management systems, HVAC controlling, or operational controlling of them, lighting as well, efficient windows, also the implementation of EV infrastructure. And in terms of industrial parks, we can consider as well the high energy consuming or electro-intensive processes that operate in the industrial parks, like manufacturing processes or machinery processes that involves a high energy consumption. And finally, the district heating and cooling that sometimes are underground piping, mostly in cities or also in industrial parks as well. So what are one of the challenges of enabling the energy flexibility for the CES is how to increase the TRLs, or the technology readiness levels, right? For example, if you increase the TRLs in one solution, you will also increase as well the energy efficiency, and you will also increase the grid interactivity and the load flexibility. In the end, these kind of solutions, speaking about the GEVs, or speaking about the community energy systems as well, you will have a complexity and integration level that will let us to improve and deploy these solutions for other pilot sites as well, and increases, of course, the grid flexibility. One of the topics that is closely related to the local energy communities is the energy storage systems, right? But there is an interesting topic related with energy storage that comes from the second life batteries as battery energy storage systems for self-consumption, right? So basically, after a market analysis from some reports of course, from the International Energy Agency, we can say that 32 million of EVs are currently on road, but also 4 of these 32 millions will be retired by 2030. And that means that 50% of these kilowatt-hour retired batteries will come from China as well, and almost 20% from the US and Europe will be retired, but it can be reused as second life battery applications or storage applications, right? In the end, we can account, or we can manage with 120 gigawatts hour per year retire from those 4 million BEVs, right, by 2030. So this is a huge market that we can explore in the end for the stationary energy applications that can be applied also for the local energy communities. So which ones are the market segments of the second life batteries applied as SES? So here we have potential markets for demand will be residential, commercial, and industrial storage as well, and then grid scale storage applications, right? But then, briefly speaking, in the commercial and industrial and consumer sector, we will have, for example, applications as HVAC controlling systems, lighting systems, pool pumps, refrigeration systems, for example. And then in industrial, we will have cold storage, backup generators, operational processes, or electro-intensive ones, as I told on the last slide for the GEVs and the industrial facilities, right? So where do the second life batteries come from, right? They come after a repurposing process that it's related to a circular economy one. When an electric vehicle reaches the end of its first life, the battery has around 50 and 80% of its capacity yet available. So in which these batteries can be collected, or the battery packs can be collected. The modules can be extracted, or cells can be extracted as well. And finally diagnosed, right? After the collecting section, you will have the repurposing process that will be packing test, or like test for the packs of the batteries to check the availability, and also to check the aging or the capacity fade and other characteristics of the batteries models, in terms of which models can be applied or reapplied again into a reassembling process, and then deploy them into new stationary energy storage systems. And that will lead us to the reusing stage of this repurposing process, right? Then after the batteries are reassembled, you can integrate these new batteries or second life batteries into these new stationary energy storage systems and provide some ancillary services to the grid or self-consumption applications, right? So this can be mostly applied into the community energy systems that we are talking about for the Creators Project pilot sites. Then some applications of this BESS are mostly in the industrial sector. We will have power quality, peak shaving, and integration of renewables in general. As my colleague Gil spoke about, like the integration of EV charging facilities, also peak shaving in one of the pilot sites, or in most of the pilot sites, sorry. As well as, for example, energy bill reduction, if we focus on the residential sector or the tertiary building sector, and energy independency, right? That's one of the most challenges that the project has, right? To have an energy independency in the pilot sites, and, well, try to reduce the CO2 emissions as well, right, somehow. Some of the potential functionalities of the community energy systems are well, based or related to these storage applications. So basically the integration of the renewables and the controlling of existing and new assets as well, right? Then the internal balancing, like self-consumption, peak shaving, time of use schemes, mostly developed there for the balanced responsible parties, right? Bilateral contracting and another controlling schemes like congestion management to network operators, and then finally, again, the ancillary services as mentioned before, like the frequency controlling, for example, the FCR, the FRR, or the AFRR, right? A general flow diagram in which we can have a brief scope of how to select or how to start from scratch a stationary energy storage system. So basically the main goal is cost minimization of these technologies, right? In the end, if we want to apply them in one pilot site or in any project that involves these solutions. So we will focus basically on having the participation from the prosumers. With this, I relate to the profiles of demand and generation of energy from these prosumers. The data gathered, for example, from the consumptions, if it's an industrial facility, or if it's a building, or if it's a community of households, right? Then time of use schemes as well. And also, for example, this will involve the potential rewards or retribution that you will have if you export the energy from these community energy systems to the grid, right? Then we will have a size range from these battery storage systems as well, and taking into account the CapEx and OpEx costs related to the storage facility, or sorry, the battery storage system, inverters, and PV models in the end, right? And operational costs. Again, with this solution, we will optimize the operational curve of this. Well, with these energy storage systems, we will optimize the energy curve from the prosumers or from the participants of the local energy community. And in the end, if everything is okay with the model, of course, we will monitor it, and also we will recheck again if the size of the storage system is the proper for the application that we are applying it, right? And then we will have an equivalent annual value of this project, or an NPV, a positive NPV, luckily, right? After some sensibility analysis. Finally, well, some future insights of the stationary energy storage systems in the creators tier 1 and tier 2 pilots, since this solution is applicable for both type of pilots. And it matters only the stage on which pilots are right now. So tier 2 pilots, as the one that we have in Castilla y León, that's the one that I'm following up at the moment. It has a level of maturity that it's advancing step by step in comparison with the tier 1 pilots that the other companies from the consortium have. But in terms of the tier 2 pilot that COMSA is working on, a brief explanation of this pilot is, well, this is the most important industrial park in the region of Burgos, in the autonomous community of Castilla y León in Spain. So it has many electro-intensive companies focused in the automotive and food, chemistry, and metallurgical activity sector. And it has an annual energy consumption of 300 gigawatt hour approximately per year, right? So the idea basically is to gather most of the companies with the higher energy consumptions, try to study the generation profiles, or also the demand profiles of them, because most of them already have some assets. And then we'll try to interconnect the existing assets with new assets as well, and deploy, and develop the concept of a local energy community inside the industrial park in the end. In the end, this will carry us a new job creation in the energy sector, as well as O&M services, energy efficiency in the buildings that we will apply this solution, and as well as monetary benefits for the prosumers, because they will have also annually energy savings on their bills as well. So finally, some of the opportunities and future insights for the SESS in the creators tier 1 and tier 2 pilots. So as opportunities, we will have, of course, the management of the energy assets at the pilots, the reduction of the external grid dependence because we will increase, as a consortium, as the solution, we will increase the self-consumption schemes in the pilot sites as well. And we will allow the balance responsible parties or the aggregators to purchase low balance energy capacity and trade it also in the wholesale markets on a future stage right now, but and then purchase real-time flexibility energy from the local energy communities for balancing services. And the future insights for the creators project are mostly the development of green technologies, tools, and assets like the SEEs, digital twins, for example, engage more local participants. In our case, as a tier 2 pilot developer, we need to involve more participants, for example, within the industrial park in a multi-scalar way, and then finally deploy this solution concept in other future project solutions across Europe. So that's all from my side, and I hope that everyone enjoyed my presentation, and well, I'm open to any question. So thank you so much for your attention.
Thank you. Thank you very much, Marco. We actually have a question from the audience. Dear Marco, which is, in your opinion, the best use for second-hand batteries? For example, providing flexibility services to the grid, balancing internal loads, avoiding congestion management at a local level?
Okay, well, it depends, of course, on the parameters that you will need to evaluate. Like, for example, how much energy you will need to, or you will need to, for example, store or the application on site of the solution, right? But for example, second life batteries, if they are lithium-ion batteries, of course, they will have a cycle or a number of cycles that can be studied before the application that you will need. But of course, it will depend on the energy profile that you will need to manage, and if you have current assets operating there. But yeah, it depends of some factors, right?
Okay, thank you very much, Marco. And we have another question. What's the difference in price between first life batteries and second life batteries?
Well, basically the first life batteries, if we are talking about EV batteries, the batteries are around 200 euros per kilowatt hour, mostly in a new basis. But as a second life battery, this price can decrease around from 30 to 50%, right? So we can speak about 70, 80, or even less euros per kilowatt hour, right? It depends on the application that you will need to use the storage system, right?
Okay. Thank you very much, Marco, for your interesting presentation. Also from COMSA point of view, that is also one of the main construction companies that we have in Creators Consortium. And I really hope that we can use second life batteries for community energy systems, because it also brings more benefits as an overall, not only on the economic price, but also in the reduction of CO2 emissions, more like on the environmental and social benefits. So I really hope we could use that. So thank you very much again, Marco. And now I'm going to leave the floor to our first in-person speaker, Julia from VAX, that will be doing her presentation jointly with Armin Meyer from EP Group. 1 second.
Good afternoon, everyone. I'm Giulia Rinaldi from Bucks & Company, and today, together with Armin Meyer from EP Group, we will present you the first, let's say, preliminary results from our work in the Creators project. As was mentioned before by the project coordinator Gil, in Creators, we don't look only at the technical perspective, but also at the financial challenges that are actually hindering the deployment of community energy systems. And as you know, energy communities are, especially talking even a bit broader than energy communities, so local energy systems are pretty, a pretty important agenda of most of the countries, especially in the transition to net zero. But the challenges are often not only technical, but also financial. This is also the reason why, indeed, there is this low adoption that Gil was talking about before. So in our work stream that is led indeed by Bucks & Company and EP Group, we are looking at what are the kind of key challenges and try to address them through new standardization and financial protocols. So we would like to start briefly by giving you an overview of the, by giving you an overview of the key challenges that we have identified in our first year of the first year of work. By also working closely with our partners and especially the pilot owners and asset owners, as well as the project investors, to try to identify, okay, what are the challenges that are actually hinder investments in the community energy systems. And here you can see a brief summary of the 3 key points that we have identified, and it's quite complex because they are actually composed by different elements. So we see the first one is the novelty of the investment concepts and limited size. So as we know, local energy community or local energy systems are usually a complex systems that is developed within current infrastructure, like the electricity network, that brings together different stakeholders with different responsibilities and also new type of responsibilities, and also assets with different lifetimes. And this is something new for the investors. It's something that usually they're not used to evaluate, and it's something that therefore increase very much the uncertainties. And despite the assets that are included in this type of projects are very much known, such as renewable energy, that is now very well known by investors, it's difficult for them to do an evaluation. That's the reason why there is a high uncertainty related to or risk, even translating to risk of technology. Then the second thing is the fact that this, again, thinking about what was mentioned before by our colleagues, there are very few systems that are actually operating right now, so that actually the practical evidence for the investor is very low. And this is something that, as we know and you might know, is key for the due diligence process of especially private investments, private financing. And also, in general, this novelty doesn't fit with the normal due diligence processes that, for example, banks are carrying out, or also any type, let's say, of private investor, unless they're more looking to innovative, let's say, concepts. So they don't fit the box, let's say. And last thing is, of course, the small size of the investment, which is, again, a very big trouble, as the return on investment usually is lower. And also the lack of replicability, as this concept, again, these concepts are very much complex and tailored to the local conditions, which don't allow to replicate the same exact things everywhere, and therefore create a pipeline, let's say, of investments that can be interesting for an investor. Secondly, all of this, of course, is reflected as also second challenge, is the complexity of the business models. As also similarly to what I already mentioned, business models of local energy systems are usually tailored to the local conditions, because are very much influenced by the local regulation, that the stakeholders that are involved, and also the legal forms that are actually applied to each of the different elements. Also, the fact that there is a lot of uncertainty related to regulation doesn't allow to really predict revenues on the long term, which is again a very big issue. And last and probably most importantly, as investors are indeed not used to deal with these concepts, and everything is new and everything is very much complex, there is for now a big lack of standardization, let's say, or like of a clear way to assess and translate uncertainties that are related to these investments into what is a risk for a traditional investor. And then last thing, which is very important as well, and that is what actually in our project are trying to deliver all together with our partners, is addressing the lack of technical capacity and also, well, financial capacity of the project developers, which usually in this case are not maybe technical project developers such as the engineering firms, but in this case are usually either local authorities or cooperatives or a group of citizens that want to move in this kind of create the local transition, let's say. But in this case, most of the time, these stakeholders don't have the knowledge and don't have access also to the capacity for exactly creating translating their concept into something that can be assessed by an investor and therefore attract in private financing. So in our project, what we want to do is try to tackle all these challenges with something that can be used by exactly the project developers and connect, let's say, something has happened, but well, I think you can understand kind of what is written here. So the overall aim of our work stream is indeed to link our service solutions that will be developed within the project. So as was mentioned, the simulation and emulation in the design phase, and also later in the operational phase, with some kind of contractual financial procedures that are understandable both for the project developers and the investors. So the main two outputs that we aim to deliver within our project are what we call protocols. So a standardized set of, let's say, tools or practices through which the community energy system can be made understandable and accessible for project developers, investors, lenders, and also the more traditional, let's say, private financing, which can assess, therefore, the profitability versus the risk in investing into community energy system. The second output that we would like to create is, once this set of templates, let's say, for simplify, which is probably one of the most important things, and standardizing these development practices and mainstream the development of community energy systems, is to make them, let's say, available to the public through our channels, and make sure that we can provide this kind of easy checklist for project developers to understand whether they're on the right track, if they're providing the right documentation for investors, and potentially, if possible, if they're on the right track, to then make the connection with the private financing. I would like today to quickly show you the work indeed that has been summarized in the first deliverable that was published, submitted actually last month, and will be soon be published. In this deliverable, we have summarized all this initial work, starting from analyzing, of course, the context of community energy systems, but especially starting to analyze the main drivers and components. So already doing some kind of first standardization of all the different models that are available at the moment. analyzing the pilots that we have in our project that were presented briefly before, and then presenting the main trends in the financing of these systems and how indeed we would like to move towards this standardized assessment protocol in our project. I will give a quick overview, then actually hopefully soon the deliverable will be public so that you will have access in our website. So we have done actually this first, tried to do this first standardization, or like classify and simplify this very complex word, as the models are very various. There are a lot of different examples. So we have seen that the 4 elements that are the base of community energy system, in our point of view, are the regulatory context, that these influence very much what you can do, the business case and the business model, and also even the technical arrangements. So everything is interlinked, actually. The technical arrangements, which exactly affect the revenues that you can access, and of also and not only the asset, not only looking at the assets, but also the integration of such assets and how they are going to be, the energy flows are going to be balanced or accounted. The organizational models, which is especially looking at the legal provisions that may underpin the organizational model, for example, the liability, the profit sharing, the holding property, and everything else. And at the end, the life cycle, as usual, financing of traditional assets is based on lifetime, and in this case, is something that in community energy system should be changed. Otherwise, as it is mainly based on social and environmental impacts. I will skip these slides just because I think we're not on time, and you have a lot of information related to the pilots already in our website, and will be presented later. Here there is a quick overview of a first example of standardization that we have tried to do. We have tried to create what we call archetypes, which is something that can help exactly simplify and communicate to the investor about our community, our system, and make it easily understandable, as you indeed put it, let's say, in a box, and you make it understandable for someone that maybe doesn't know much about what you're doing. So this is a first example, is a work in progress, because it's also the market is moving fast, things are changing practically every day. So this is just a first example based on exactly on the current situation and the broad analysis that we have done related to all the community energy systems that are currently being implemented in Europe. What we did is to then start analyzing indeed these core components that we have talked about before, and apply them to practical cases, which are our pilot sites. And so we have really studied what are different elements related to regulatory context, technical arrangements, organizational model, revenue streams, and life cycle. And for each one of them, we have also identify and evaluated what are the current uncertainties, because this is what allow us to understand, okay, what are the big uncertainty that someone external to the project would see, and how can we address them already within our project. So we have done this work for all the 4 pilot sites. This is just an example for the Temse site. The rest, the other 3 I will not show because otherwise it will be too long. But you can see here indeed the example of the elements that we have identified for each of these key components, what we call. So for example, for the regulatory context, there are 3 core components that are the energy community regulation, the network tariff, and the energy prices, as well as the market accessibility. And related to these elements, we have analyzed together with the pilots and the stakeholders, okay, what do you think are the big uncertainty for these elements? So, of course, it's very much related to, again, regulatory uncertainty most of the time. So what's going to happen in the future? But really looking a bit farther, for example, related exactly to the business case, what would be the change that would actually impact their current analysis. For the technical arrangements, we see, for example, related to the current performance of their technologies, that some technologies are very innovative. So of course there is still a lot of uncertainty related to their performance, whether actually in the future will be possible to share energy between neighbors, and also a big uncertainty related to uptake and anchor organizations. So how many organizations will actually buy in the model. Related to the, let's say, organizational model. So who is going to take different responsibility and liability also in this system? Cordel, for example, will be the manager. In this case, is the manager and the sponsor of the current pilot site, but in the future, exactly something that would be brought to market. So there would be other stakeholders to be involved, but. And the uncertainty is very much related, okay, what is the current size of the possible market? And also, is this value proposition going to be competitive with the current, with the normal energy supplying companies, let's say, because sometimes exactly the economic savings will not be enough to attract the consumers. So what else can be provided? So all this work has been done also for the other 3 pilot sites. I think if we will share this slide with actually you will see this work anyway in the report. So now I will pass the word to Armin to present the main findings related to the trends in financing and our future work on the protocols.
Thanks, Julia, and hello, everyone. Pleasure to be here. Can you hear and see me okay? Okay, thanks.
Yes, we can hear you.
Great. So Julia's already covered off quite a lot of these, actually, in terms of certainly looking at topics like complexity, because of the variety of projects out there. Certainly there's, as it says here, there's a lack of standardization across these projects, and we know that quite well. And this is similar. This issue is not alone to community energy systems or microgrids. It kind of spans across the ESG space or the net zero transition, in the sense that it's a new world and there are lots of small projects, small ideas, innovations happening, and sometimes there's lots of complexity. My background personally is very much in buildings and building energy efficiency, and this reminds me very much of the challenges that are faced when doing major retrofits, complex buildings, and financing those major retrofits, where there are lots of issues around things like data quality, but also being able to compare one retrofit to another and standardizing across projects. As a result of that, there's actually still a lot of public funding, going into retrofitting, and it's likely that the same is true for CES projects, at least in the near term, because public money can help to alleviate the costs which are associated with the complexity, which is associated with risk, so to provide some assurances to the market and get past that sort of innovation valley of death, as they call it, to wider market scaling replication. Complexity we've discussed, and you can see it already in the slides that Julia was sharing. The complexity is evident just within creators, and if we go further afield, every project is different. Risk is key. I would say that for a lot of investors, risk is a term that's, let's say, used every 5 minutes. It's critical to understand what the risk level is, because that's how you price a project in part. So part of the risk is perceived, part of the risk is actually real in these projects, so we need to be able to quantify that effectively. Obviously, there's a limited availability of financial products, which although I should caveat this by saying, and you can see it in some of the projects going on already, there are instruments available. You can do a power purchase agreement. You can do a hire purchase agreement. You can lease equipment. You can have, straightforward investments using capital expenditure, but that's typically on individual aspects of a microgrid or a community energy system. So somewhere someone has gone and funded a solar installation, possibly using a feed-in tariff or rebate. Somewhere else there's a CHP system financed with another mechanism. And it may be that actually that is the way forward as well, and that's what the longer term will look like. But the idea as well is to create bundled instruments, instruments that can be more easily applied to complex projects. And of course, all this is quite novel, and the novel part is the fun part. So it's really fun to talk about battery storage and the possibilities that the technologies represent and the integration of those. But I think our focus here in the project is more on the boring side of trying to put together the documentation required to support these projects. I'm just putting in the chat a link to the Investor Confidence Project, which Stephen Fox, who founded Energy Pro or EP Group now, was closely involved in, and notably the project development specification, which is more related to, let's say, large-scale retrofits in commercial buildings. But there's a lot of overlaps here, and it's a good precedent in terms of what we're trying to develop with the protocol. Next slide. So again, we've kind of touched on this in multiple ways, but the idea of a protocol really is around, there's lots of banks or lenders around that have made commitments, and you don't have to look very far to find almost every day a new ESG or net zero transition commitment by lenders. The challenge will be to translate that into actual monies lent and invested. On the ground, that amount is probably quite limited still. And perhaps at the level of a CEO of a major bank, you will have lots of good ESG commitments. But when it comes down to the analysts, the underwriters, the risk assessors in a bank, they need all the documentation that they require. They need it on time. They need it in standard formats. So there's lots that needs to be done to shore up that and to make these kind of projects more palatable, not just to C-level executives, but really to the key middle management layer and financial institutions that need to be able to process these kind of projects, that need to be able to put them through their standard application process and risk assessment process. At the moment, we're in an early phase of this, I would say, although we have lots of insights, as I mentioned, the ICP project, but we have a lot of basic elements for this. So there's more to come on this, and we haven't really put much here in the deck just because limits of time, but also because we're currently developing this. And I think, as Julia will mention, we are looking also for experts to join a working group to help us develop this in future, to sense check what we're doing, to review early deliverables, so that we develop a protocol that is really fit for purpose. And I think I'll stop there and hand it back to Julia. Thanks very much.
Thank you, Armin. Here, well, I think we are a bit over time, so I will, here on these slides, you can see the conclusions, which actually summarize all what we already presented. So indeed, the importance of protocols and in the deployment and the financing of community energy systems. And as Armin just mentioned, just to finalize the presentation, indeed, we are now in the work that we are doing on the protocols. We would really like to actually have experts working potentially in other sectors or in this sector as well, but like either investors or even on the technical side that work in the development of these projects, so that they can actually directly contribute and test and validate the work that we are doing related to this. Because our objective is to actually develop something that can be used and adopted by investors. So that's the reason why we want to have direct contact and have direct contribution through this working group. So if you know anyone that could be interested, please contact us. And I think that's it for now. There was a question.
Yeah.
I think.
yeah, we'll let Blanca, but if you can stay here. Okay. I just want to show it to the audience over here, but it's not here clearly. But, so, okay, the question.
Start responding because I see the question there, and it's interesting because we had the same question come up in our own General Assembly around life cycle. I think really what this refers to is that in traditional, when you're purchasing an asset, it will depreciate over time, and you look at the lifetime of the asset, and you look at simple metrics, like simple payback of an investment. In community energy systems, we need to look at a variety of other factors and try to also calculate the positive benefits on environment and society, and looking at the project in a whole more holistic and life cycle sense. I don't know if you want to add anything there, Julia, or others on the panel, perhaps. I don't know.
I think it's you answered already. Thank you very much. I will leave the floor to Blanca again.
I have one question. I have one question.
Okay, we have one more question.
Sorry, Julia, but you just sit, but maybe I will ask you to come back here, but maybe also Armin can reply to it, because you both spoke about investors in general in your presentations. I would like to know more in details, if you already know it. Yeah, which are the people that you are targeting the most, or the people or the association or the whichever actor that you think it's the most important and most feasible to invest in this kind of projects? And well, if you thought about involving this funding, new ways of financing.
I didn't hear the second part of the question very well. Could you just repeat the second part, please?
Yeah, if you included in your analysis, or you will include in your analysis, crowdfunding aspects, so a bottom-up approach with the same users, or also external users and general audience, let's say, that can invest in energy community projects with minimum participation, let's say.
Excellent questions. Maybe firstly on the crowdfunding, it's probably a really interesting opportunity because certainly those people who support crowdfunded investments are going to be presumably local, or will be really engaged and will be benefiting on the social and environmental side from such projects. So I think there's a lot of promise in there. It's probably maybe just a challenge of combining crowdfunded investment with additional investment. So just structuring the instruments around that, but it's certainly a key factor. On the types of investors, I would say there's probably, if you're going to market with something like this, it would be an obvious first step to look at investors who have a stated commitment to supporting ESG projects and who are active in this space. And in a way, they will probably be more, let's say, tolerant about differences and levels of complexity, and they may be able to absorb a higher level of risk. So that, so the crowdfunding target audience is very interesting, and the sort of really pro and vocally pro ESG investors is certainly another target audience. I think for us, the challenge and for the wider market is the more, let's say, traditional investors who are risk averse and who are accustomed to what they're accustomed to. And it's about making this sector more attractive also to that segment of investors.
Yeah, thank you. The fact is that, as Julia was explaining before, you have to show them that there are already projects developing that are working in that sense, and that there are returns of investments that are being given to the investors. So how do you think to overcome this thing? Because we don't have enough energy communities projects that are already developed that are allowing us to show to potential investors that we can do it and they can be safe, their investment can be safe.
I think we're still, the market's at an early phase, and creators, I think, is probably really at the forefront of this. So more of these kind of projects is what will be needed. We mentioned public funding in the presentation. I don't see this market getting off the ground without significant increases public funding as well for these kinds of projects, or continued R&D funding. Europe is doing okay, but probably other regions per capita R&D spending is higher. So that's an important consideration.
Thank you.
Okay. Thank you, Julia and Armin, for your presentation. And I apologize for some technical problems that we've had, but I hope they are solved now. I am for giving the perspective on community energy system from a business financing point of view. Thank you very much. Now I'm gonna invite Boris from Joseph Stefan Institute to share his screen and do his presentation. Thank you.
Thank you, Blanca. Thank you, everybody. I'm really happy to be today with you. Blanca, I would like to ask you to share my presentation directly from your computer, because I think that I have some technical problems in sharing my screen. So yes. I think it would be much easier if you share it. To the audience, I'm really sad that I'm not with you in person during this session, because my heart is in your city, eternal city of Rome. Io sono il grande romanista. And I hope that the next time when we will have this kind of conference, that I will be together with you in Rome, or whenever this conference will be held. The title of my today's presentation is Local Energy Community as a Platform for Sector Coupling and Connecting Energy-Intensive Industry with the Neighboring Communities. It basically came out from the idea of helping energy-intensive industries to overcome certain barriers, and also to connect with the local neighboring communities. In case of Slovenia, it's vitally important also for reaching the 2030 target and also 2050 targets. Next slide, Blanca, please. Next slide, please. Okay, the content of my today's presentation is, I will try very briefly to present you the relationship between my institute, the biggest research institute from Slovenia, and the Slovenian Steel Industry Group. Also, I will give you the description of the pilot plant. I will provide you with the general view on about the community energy systems from the Slovenian perspective, and also to briefly introduce you with the just transition and the key development challenges of energy-intensive industry in my country. I will present you identified use cases and the complex modeling of which is necessary for the implementation. Of course, performed activities and future challenges will be also presented. Next slide, please. We have at the Josef Stefan Institute, we have a long tradition of partnership between us and the largest steel producer in Slovenia. With many already implemented projects. We are really proud that among them is the first excess heat utilization project, which was not implemented at Siakroni, but in other location owned by the Slovenian steel industry. With that project, we connected the energy-intensive industry with a local district heating operator, and on the annual level, around 9,000 megawatt hours of the excess heat is utilized and inserted or injected into the local district heating system. We have an excellent cooperation with also other partners from the Slovenian industry. Slovenian steel industry is the leading EU steel producer in the niche market. That firm that we are working with, Siakroni, is firmly anchored in its local and regional communities. It is basically the guarantee of social cohesion and stability in the region. Blanca, please, next slide. Just brief introduction of the Slovenian Steel Industry Group, entire group. It is not presented only in Slovenia, it is also operating in Italy, also other Western Balkan countries, Germany and the United States. It is vertically integrated business structure. They actually have a complete control of the value chain from the scrap metal to the final products. It is, in this moment, it is very important to mention that they are not producing steel from the iron ore. They are producing it from the scrap metal, which means that they are, at the very beginning, they are sustainably oriented towards sustainability in the steel manufacturing process. Next slide, please. Just a few details about the company, our pilot site in Slovenia. The basic facts from 2019. This is the biggest producer, Slovenian biggest producer of the flat rolled steel products. They make around 300,000 tons of finished products, which are transformed into around 430 million euros of revenue, around 1,400 employees. They have a really strong R&D department, especially one dealing with chemistry. They are proud that they are certified according to ISO 50001, 40001, and many other standards. What is important to mention is that they have a really long tradition in steel production. In 2019, they were celebrating 150 years of industrial steel production. Next slide, please. From the point of view, from the Slovenian perspective, the community energy systems are the key for us to reach the target of 2030. As you know, we are the neighboring country of Italy, a bit smaller than Italy, of course, almost 30 times, if I'm not wrong. But we are really proud on our environmental protection. As you know, the Natura 2000 is all over Slovenia, so it is very hard to put any new energy-related project into the space. And in that context, we think that there is a huge potential in local energy communities for connecting local inhabitants, network operators, energy-intensive industry, and the energy service providers. You can see also the goals of Slovenia regarding the 2030 targets. That is something that is taken directly from the Slovenian National Energy and Climate Plan. As I mentioned, local energy communities are in the heart of the Slovenian National Energy and Climate Plan. All those 4 ACEs, we call it 4 ACEs, local inhabitants, network operators, energy-intensive industry, and energy service providers, are considered as a key players for reaching those targets. Next slide, please. In the context of data collection and community engagement at the site of Siakroni, it is worth to mention that it is one of the biggest Slovenian energy consumer. They are consuming 350 gigawatt hours of electricity and 450 gigawatt hours of natural gas annually. They are connected both on the electricity and natural gas transmission system. They use also technical gases. 2 modern and efficient CHP units are also installed at the site. Company produce almost 3 gigawatt hours of electricity and 4 gigawatt hours of heat annually. Next slide, please. Also, as a first step in our work, what we have done, we looked also for the potential site where our concept and creators approach could be replicated, and we are really proud that modeling of industrial emissions from industrial emissions excluding electricity, which means that we are speaking about direct emissions of CO2, when we have done that modeling on the municipality level in Slovenia, and we have, based on that modeling, we have identified several locations which are potential, which can serve as a potential replicatory or replicator location for the creators approach. We are happy that one of them is already signed some documents with us, and they are willing to be part of this story because they see that energy communities can help energy-intensive industry to survive the challenges of climate neutrality. Next slide, please. In this context, the main challenges of Siakroni, which is participating in the project, is of course how to remain leading steel producer and how to further strengthen its leading position on the local and neighboring markets. Of course, it is also for them very important how to connect with the local municipality and become a hub of the future energy community. In this context, they see the waste heat utilization as the key aspect and the key element which will open the door of future energy hub. Of course, it is always a question how to sustainably increase the production capacity and continuously enhance environmental, energy, and economic efficiency. In this context, resource efficiency has been recognized as the very, very important element of the global policy of the C Group. Next slide, please. Having all this in mind, we have tried together with the colleagues from Siacroni to identify the use cases which will be relevant for the Creators project. Of course, the first one was the excess heat utilization in close cooperation with a local district heating operator. That local district heating operator from the very beginning recognized the potential of this cooperation, and we are really progressing well in this case. Also, the other case is generation of the renewable electricity and better balancing of electricity consumption. I must say that with the help of other members of the consortium, we managed to make a really significant step in this case. Also, this is also very important for the entire steel industry in Slovenia, because they are all of them are planning to utilize their roofs for the PV production of electricity. And in this case, the produced electricity will not be any burden for the electricity distribution system, because everything will be consumed at the location. What is also interesting in the case of Siacroni is that if we are thinking about entire valley or that small part of Slovenia, the location of the factory is actually the optimal location for the PV production in that region, which means that all local inhabitants who are thinking about putting the PV on their rooftops, they should be aware that better numbers can be gained, or more electricity can be produced on the rooftop of the Siacroni. The third use case is production of green hydrogen. Green hydrogen is a big story when we are talking about green steel, and this is also very important for the future development of and future greenification of the steel production in Slovenia. Next slide, please. To put this in numbers, Siacroni plans to implement up to 5 megawatts of rooftop PV. I hope that we will reach these numbers very soon. Certain testings are already has been done, and we are still monitoring and evaluating potential from different roofs. Of course, during this project, we are proud that we have identified the potential for the small hydropower plant, which can be installed at site. Actually, our first estimation was around 15 to 20 kilowatts. We are proud that we managed to find a way how to utilize even more. Now, the numbers that we are now operating with are showing potential up to 150 kilowatts. Of course, hydrogen production, there is a potential for small hydrogen facility that can be installed on site. It is also compatible with the Slovenian National Energy and Climate Plan, because all the extra hydrogen that could be produced can be also utilized locally for the supplying of the buses or the public transportation in the region. And also, if there still will be excess hydrogen, it can be directly injected into the national transmission system of natural gas. Waste heat or excess heat utilization, Acroni plans to utilize approximately 25 megawatts of low-grade waste heat from the cooling circuits. In this context, we are already working on one part of it, which has a potential for about 1 megawatt of the waste heat, but operating hours are higher than 6,000 hours per year, which means that at the end, from that part, we will be able to utilize around 6,000 megawatts hours per year. Next slide, please. We have installed several PV testing facilities. That real data is used for the evaluation of available locations, different maintenance practices, and selection of the optimal setup. That data is included in the Creators platform. Next slide, please. The results that we have got shown us, for instance, the influence of different operating and maintenance practices on, for instance, in this context, cleaning sequence, which means that if we don't apply an optimal cleaning sequence, we may lose around 25 up to 30% of the produced green electricity. This is the reason why such project like Creators has helped us or has a great potential to help other locations to also to check the availability or to do before going into the real investment, to check and get the real data, which can be also very valuable for the final stakeholders who will at the end decide to provide the financing for this project. Next, please. Our modeling has been based on the process integration approach in order to systematically optimize the energy efficiency of the complex industrial processes. Waste excess heat from the steel plant has a potential to provide the proper substitute for the I'm sorry, currently used natural gas, which is used for production of heat in the local district heating system. I will show you in the continuation of my presentation a few basic models that has been developed. We are still working on it, and I hope that in the coming months that we will be able to have the first results about the compatibility of the steel production and operating hours of the local district heating system. Next slide, please. Like I already mentioned, the geographical position of the steel plant is the most suitable location for the installation of the big rooftop PV plant in the local municipality. Hydrogen production, this is the story when we're speaking about steel industry. The hydrogen production goes hand in hand with the steel production because it is used for the reduction. And also we are proud that the hydro potential is higher than it was initially estimated. On my next slide, you will see the results, the first feasibility results of and this is actually sensitivity analysis of the installation of the hydropower plant, small hydropower plant. The numbers are really, really great due to the, of course, once again, higher operating numbers of the hydropower plant, because we are utilizing already existing infrastructure, which means that this kind of project, which can last up to 100 years, will have a payback period. First numbers are showing the payback period of 8 years. Next slide, please. This is something that I have to put in all my presentation, because I'm coming from the research institute, so we like to make simple things look very complicated. That's our job. This is the first model of entire factory. It is the approach, top-down approach. We have analyzed all the existing systems. Those that are glowing are future systems that have a perspective to be added into the complete story. Next slide, please. Here we are showing how we connected all those, for instance, heat sources, heat with the sinks, how we are connecting the flow of materials with the energy flows throughout the company. This model is based on the energy cost center methodology, which, as I mentioned before, it's part of the process integration family. Next slide, please. And we go further on into the details. Now we are analyzing the specific process, looking for the transfer functions between energy use and availability of excess heat. Next slide, please. And this is the final step when we are reaching the final numbers and the final elements in the entire model. As you can see, it's quite complicated, but it is the only way how we can be sure that time steps of the steel production and the district heating needs are properly connected. Next slide, please. From the point of view of Jesenice local energy community, which will be, I hope, very soon also implemented in practice. The simulation and emulation of the potential future situation is very, very important, and especially those related with the excess heat utilization during the creators projects. I must say, and here also always I would like to share the floor with my colleagues from Typhoon Hill and AECOO, because without excellent cooperation with them, some of these numbers or some of these things would not be able to present at this conference, and also we will not be all alone. We will not be ever able to develop such a complex models and such a complex such a complex evaluation tools. I have mentioned many processes that have a potential for the extraction of the excess heat. One of them, called rolled non-oriented, in our language we call it CERNO, but in English it's called rolled non-oriented, is the thing that we are dealing the first. I hope that by the end of this year that actual implementation work will start, and that we will start to utilizing that potential of 1 megawatt of excess heat. Next slide, please. At the end, of course, for us, it is very important to have the enhanced forecasting capabilities, because in this context, we will have a potential to avoid substantial cost increase. The results of the preliminary analysis are very promising. This was the step where the cooperation of different entities throughout the European Union show actually the full potential, because at the Josef Stefan Institute, we have got the same results like our colleagues from AECOO, and the third independent company who was evaluating both results confirmed that all of us reached the right numbers. And of course, those numbers are showing that there is a great potential, and that is the reason why you saw on my first complicated picture, you saw that there is a glowing element showing potential for installation of 5 megawatt, an additional battery of 5 megawatts. Of course, there is also economics of green hydrogen. This is something that we will work very hard in the coming months, and of course, all this must lead to the improvement of the environmental footprint of the Siacroni factory. Next slide, and I think this is the part that I like the most, when I have to say that thank you very much for your attention. It was a great pleasure to be with you. Unfortunately, I'm not in Rome, but next time I promise, if you will organize this conference anywhere around Europe or around Slovenia, I will come. If it will be in Rome, I will walk to come. Thank you. Blanca, you must, okay.
Yeah, thank you very much, Boris, for your presentation. In fact, our pilot site in Slovenia is very interesting, and it combines a lot of different energy assets, and there is a lot of work to be done. So yeah, I think with creators we will be able to do really good things in that site. Thank you very much. I would like to take a super quick break now, but only 5 minutes, please, because at 5:30 the next conference starts, and we should keep on schedule. So let's take a short break, and let's be back in 5 minutes. Okay, thank you. Okay, can you hear me now? Okay, sorry, we're having
Yes.
technical issues here in the room. Okay, let's proceed. Since I mentioned there's another conference starting at 5:30, so please let's keep in schedule. Now the next speaker is Igor Kovacevic. So please, Igor, floor is yours.
Just a moment. Can you hear me?
Yes.
Hello, everybody. It's my pleasure to be with you, and I will try to be fast, and as I will try to be also successful as my previous speaker on Creators project. Today I will speak about simulation in Creators project, and this is only part of simulation emulation engine, which will be later presented by our colleagues from Typhoon Hill. I'm coming from AECOO, and I will explain which company is, and my name is, I'm located in Belgium right now. Today, my presentation is quite straightforward, which means only a few chapters. I will just explain briefly what is our strategy in simulation, optimization, and control of energy technologies in very various systems. I decided today to present only two cases. Actual in a Creators project. I will explain briefly about only one technology in the Port of Barcelona, and also Cordel. Also, I will be free to share a few examples of what is our vision and what is next step that we are we'd see in the next 2 years, which will be realized on Creators. At the end, I will conclude some things. Yeah, at the early beginning, I would just want to share a few things about AECOO. You can see information on web page, and we are proud to say that we have more than 5,000 buildings already in our database. All this information are related with energy, and our company want to offer different energy services around Europe, and right now I will focus on the design of cloud energy management system, what we are developing in the company. Just recently, together with the Basics, the biggest, I think, construction company in Belgium, and also Proximus, leading mobile operator in Belgium, prepare and they invest some money in our company, and now we are planning to achieve really very ambitious goal in energy field, and we will soon or later we will change our name to AECOO. On the first, I will just briefly explain about the strategy. It is quite common strategy for engineers. We are doing with model predictive control. Two things I want to emphasize here. We are optimizing something in horizon, which is moving in the time, and as a result of we are enabled to collect all technology information or energy information inside, and as a result we will have some kind of optimization, optimize scheduling of controllable device which is in place in this observer system. Yeah, just very simple basic example, and proud to say that such example is in our company is already in simulation of on number of hundreds. We are dealing with 4 component system. We call this grid, battery, home, and PV system. And what we are doing, we are simulating what happened with demand or PV generation, and as the result of the optimization, we want to make the optimal schedule of battery, all in order that grid cost will be minimized. And the last slide about this, it's actually classical optimization problem. The most simplest function that we are using, of course, is not always the case, but now I just, in order to present that we are minimizing the cost, cost is actually related with the power that you are spending and also the price that you have during the time. And in order to make that, we prepare some constraints. Here is just a few examples about what we are doing with the battery, the more simplest example that we are using. This is simple mathematics, but now I will focus on what we already realized in Creators project, and what I mentioned. Actually, we are going in only 2 locations in the Tier 1 project. First of them is Porto, Barcelona. We are proud that we receive information about fish dock in Porto, Barcelona, and you see the schematic presentation of this dock. Idea is to actually analyze what will happen if 6 or 7 consumers participate on local energy community. And on top of that, they are planning also to install some roof PV generation and also some additional flexibility, maybe a stationary battery, but also our task is to analyze what will happen if we use the ice factory, which is the major consumption this local energy community. What will happen if we want to control in smart way, all in order to increase self-consumption on the field and also to reduce local energy grid electricity cost in total. Just one example about, we receive all documentation thanks to local partners, thanks to COMSA. We receive actually current strategy of ice factory, and you see that ice production is dominant during the summertime, but also you can see that they are doing 3 nights in the row in order to fulfill whole storage of ice factory. And based on the fact that they want to install the solar and they want to actually change the logic on ice compressor inside the refrigeration system, all in order to actually increase self-consumption, what I mentioned before. For that, we prepared a lot of models, different models. One of them is about ice storage system and also one for refrigeration system. Not going in details, but based on that, as a first step in simulation, we receive also, thanks to local partners, we receive all information about electricity bills and all the contracts that they already have with the local supplier. And the result of this is here. And what is our first task in simulation is actually to tune the model in order that we receive similar results what we have in place on what we receive exactly from electricity supplier. And the last slide of this, I want to say that we prepared the model and we decided that the ice factory is driven by smart, by model predictive control, and on top of that we installed the local generation. And on this graph you can see that actually if we have local generation during the day, our system are enabled, actually compressor in the refrigeration system will follow the extending the generation of the field, and all in order to protect and to stop on to minimize the self injection on the grid. And you can see here, because of compressor's size is quite high, actually we are able to demonstrate that all energy that will be produced on the field will be consumed in ice storage system. Here is the some results, and I can say that in comparison with reference, in classic case, what we have now, we are able to reduce total electricity consumption for more than 35%. Second example, I will just spend a few minutes about Temze. Thank you, Hill, that you presented very nice, but also I want to share that we are really proud that we are participating on this project. Yeah, and one of the projects is also to control this very nice building in dock of Temze. But today I will just briefly explain what we have there. It's a lot of technologies, a lot of playground for us to a lot of playgrounds that we can play our games in this energy service field. And just to mention, we have a lot of different technologies. In total, I think we have 2.5 megawatt of PV already installed on the roof. We have a lot of different chargers already in place, also V2G, vehicle to grid chargers. But what also Gil mentioned, we are planning to install water tower and tidal turbine. Next slides, I will explain more about tidal turbine, but just to mention once again, you see the schematic presentation of different technologies, and today I will focus on tidal, but of course we have some results about pipe storage systems and the battery and all local system. The all local energy community consisting of 5 buildings, or 4 of them is PV, and you see a lot of chargers around. Yeah, what I mentioned, I'm talking now about tidal turbine, and I'm really proud that actually see the potential of turbine of a renewable potential on this location is driven by fact that Schelde River close by is actually changing amplitude or level of water up to more than 5 meters every 6 hours. And here is really measured data of Schelde River in time. I think it was 15 days window, or I don't know, maybe in 2021. And this is actually driving force that we think to, if you see here, we have a dock, and this dock is actually old shipyard, and the plan is to install the turbine in the gate of this dock, all in order to actually use this renewable potential to produce electricity when the Schelde River is going up and down. I'm really proud to say that we developed a very comprehensive model thanks to Turbulent guys from also partner of this project. And the proposal is that we install even the turbine of 200 kilowatt. And this turbine, it's based on Vortex turbine, very unique technique, and they are doing around Europe and around the world such installation. But for me, it's more important that they are actually using the electricity generation in both direction, which means that during the Schelde River going up or down, we are enabled to produce electricity. Here is one example of one period. On the blue line, you see how Schelde River is going in time. As I mentioned, this driving force for electricity generation, and the red one is actually dock level. And here you can see during the beginning time, nothing happened. When the Schelde River is enough higher than dock, we start with the generation and actually produce the electricity in this period. And you see the dock is charging, and after some time you see, based on physical phenomena, Schelde River is going down, and we are stopping production. And after some time, when the dock water level is become more than Schelde River, we are able to produce once again electricity. This example, is very nice that I wanted to share with you. And maximum power here is, you see, 181 kilowatt. If we install this turbine on the place, we are proud to say that our capacity ratio is about 2,800 hours per year. And we implement this in our simulation tool. And you see here on the left-hand side that this Vertex turbines, it's quite unique, which means that the actual electricity is produced on a normal pressure, and it's very good regarding the natural aspect. But on the right-hand side, you see what will happen if we install such turbine right now, 2020 here, and on the green, on the brown, you will see how much injection we have in the place, and the idea is to install this turbine and on this
just
turbine.
in the background.
Sorry.
We're hearing some noises in the background. I'm not sure.
You don't?
You don't hear them? Yes.
Yes, we hear.
Maybe, Alexander, can you close your microphone?
It is closed. It's just you don't see it as closed. It has a off switch on its own.
Can I continue?
So maybe Igor, they are the headphones that are making this noise. If everybody's listening.
No. Okay. We can hear them now. And sorry. Let's.
No problem. Oh, yeah, and here is the calculation, and we are from financial aspect, we actually analyze what will happen if we install such type of turbine on the place, and we calculate this on annual basis, and we make life cycle analysis of that. And I hope, and I think what I heard this week actually, that the investor in this example, Cordell, will go on with this project, and very soon we will have installation of such system, and my pleasure will be actually to continue to control such very unique system what I present now. And just few steps about what we are planning in the future. Yeah, thanks Boris for very nice presentation, and I did not have time to present a case about Acroni. Next time I promise that we will have such. But from general perspective, I just wanted to say that I presented 2 examples about simulations, and what I mentioned at the beginning is just part of simulation emulation engine. But from our perspective, just few steps will be presented to see how this simulation is going in real control or digital twin. If you want to go in real life, yeah, first thing you want to develop is a forecasting service, and here I'm proud to present to you what is our company is already developed. Here is an example of Belgium. They had electricity market, and we have a real life microservice where we are every time in position to see a lot of different machine learning algorithms, all in order to very good quantify the future of electricity market in Belgium. And this will be extended also for Spain market, also from Slovenia and so on. And but yeah, this current state and what I see as the next step, what I presented in simulation, we are doing offline thing, but if you are going online, we are able to produce such kind of things. And here, once again, you can see various of forecasts, all based on machine learnings, and all this information is already in database. If I want to implement any project about the ahead market on Belgium, I am already in place to see what is the forecasted electricity price. And last slide about this is another project which is not related only with creators, but of course I'm expecting that this graphs for next 2 years will be more related to creators and pilot projects. But here we receive information about already control of battery in one shop in Belgium, and you see on the red line what is the real grid consumption or injection grid balance if the battery is working as such. And here is with the dot line what we are proposing with implementation of MPC model predictive control and relatively advanced grid models. We are in position actually to make much more peak shaving than it's now in place. And on the table you see the difference. We are actually in position to make some kind of controls, but this is not control is not in place, and we call this somehow shadow mode. But this kind of things I'm planning to have more and more about creators project in future, all when we receive online data in our database. Right now I can say that just we receive some data, but still we are waiting integration of receive live data from site location, which is presented by here. At the end, I just wanted to say, we implement model predictive control strategy for simulation controls, various technologies. We presented 2 examples in Porto, Barcelona, where we use storage system as a flexibility for for whole local energy community. And the second example, I presented quite unique approach of Tidal Turbine in the ZAT location. Yeah, I can say simulation, but also in optimization based on MPC. We demonstrate that it's quite useful tool for investment decision. Not only in Creators project, we are active on commercial things around the Belgium, Netherlands, and Spain. Also, very active on other European projects. And the last thing I want to say, simulation is just integral part of a digital twin, what we are planning to do with Creators project. And I'm really proud to be part of this team. And I hope that Guy from Typhoon Field will continue and explain more about our strategy on the Creators project. Thank you very much.
Thank you very much, Igor. Indeed, our next speaker is here with us in Rome. Is Ivan Todorovic. So I will leave the floor to him.
Yes, come on. That's fine.
I'm not sure that's the one.
It's this
Should
one.
be on the desktop.
No, era the energy citizenship.
Should be on desktop. This one.
It's this one? Okay,
Yeah.
perfect.
Hopefully. Now we should also start it with that strange presentation, but non-present.
It's
Yeah.
you can.
Yeah.
It's fine.
We can try.
Okay, wait. Okay, let's share it. No.
It's not us. I think so, yeah. Is it that?
Yeah.
No.
Hopla.
Yeah, but I want it to, change the configuration.
Here?
Yeah, that's it.
Perfect. Just click and that's it.
All right. Thank you everyone for participating, being here, and for you who are participating online. I'm Ivan Todorovic, and I'm going to talk a little bit about the digital twinning in the domain of local energy communities in front of the Typhoon Hill, of course, in the context of Creators project. Okay, so the Typhoon Hill is a company that is providing the users with the hardware and structure tool chain for the controller hardware in the loop, and generally for hardware in the loop development. That is our core business, and our core product is or are the emulators that are used for multi-domain real-time simulation of the electrical systems. And nowadays, within our emulators, we can execute the models that are consisting of the power electronics devices, electrical machines, electrochemical devices, power systems devices or elements, and so on. Consequently, the emulators are used really in a wide different range of applications in drives, and generally in drives, and particularly in the e-mobility, energy storage, microgrids, more electric aircrafts, marine applications, and so on. But moreover, the Typhoon Hill is not anymore just a company that provides the real-time simulation tools, but also we are providing the users with offline simulation. So essentially, the models that are developed in our toolchain can be deployed essentially both on the emulators and also on the users' PCs. And as you have heard, and as you will see briefly in this presentation, and in more details in the presentation following this one, that will be given by the Alexander Kavgic, you will see that we are also going to provide some cloud services. So in broad terms, Typhoon Hill is a company that is providing the users with a digital twinning platform in domain of electrical systems. So this is what we do, and who we are, and in the next 10 minutes or so, I will present you how we do it, or how we can go on doing digital twinning. So the old way is the way in which we have been using the simulator tools, so standard simulation tools installed on our PCs. The advantage of this approach, of course, is that many of those tools are now already available. The community that supports these simulator tools is also developed. There are many examples and tool chains developed. Perhaps the most important advantage of this approach is that we can really do detailed modeling. But the serious disadvantage of this approach is that we cannot do real-time simulation. Actually, the simulations that are made by in this approach, model-in-the-loop approach, are significantly slower than real-time. And also, we get only a rough idea of how the systems operate when we employ model-in-the-loop approach. Next one is called software in the loop. It is different from the previous one in the sense that the control code or scheme isn't anymore made out of the blocks that are coming with the installation of the simulation tool, right? So in previous case, in model in the loop simulation, we are essentially making both power stage and control schemes using the essentially same blocks. But in case of software in the loop approach, the control scheme is essentially implemented using the some embedded code language, usually it is a C language. So this is essentially a convenient way to see whether the code that we are developing is going to have some organizational deficiencies, or whether it's going to have some syntax mistakes and something like that. Of course, we are also talking about the offline simulation, so we are still talking about the PC implementation, and consequently, this is really something that slows down the development. And also, we need a dedicated compiler. Sometimes this is not really readily available. The third approach also belongs to this old way of doing digital twinning, is called the processor in the loop. And in this case, the code is really employed on the real controller. Although we are not really using all of the peripherals of the controller, we are using just the processor. So the code is downloaded to our processor, and the simulator with the power stage that is implemented, as in previous two cases, is communicating with the said processor, of course, in non-real time. So essentially, the controller board is slowed down by the offline simulator. In this case, also we need some specific tool chain, and also we are talking about significantly slower than real-time execution. But the designer is really aware of how the processor resources are going to be utilized. So this is, of course, an advantage. Now there is something that has only recently emerged, and to the best of my knowledge, it doesn't really have a name. I call it controller in the controller model in the loop. So some of the vendors are providing users with a behavior model of controller. So essentially, within the simulator, you can really see how the complete controller is going to behave once deployed, once the code is implemented in it. So we can see how the processor is going to be used, how the memory will be utilized, whether we are going to have some overflows, and so on. And of course, this is again the offline simulation-based approach, and since it is focused on controller and so how the controller will behave, this is not something that is particularly important for local energy communities. Now, this is something completely different, essentially, and something that is really interesting for the local energy communities. And actually, it is weapon of choice for most of the engineers that are involved in the power electronics and power systems design. Nowadays, it's not present-day tool in a sense that is developed recently. It has been developed some 20 years ago, usually, depending on the vendor. But it is used nowadays, and it's a really popular tool. It is based, of course, on a dedicated hardware, emulators that are really made and designed so that the power stage can be executed in the real time. So it's not really a PC general purpose platform, it's a real-time simulator. The power stage or the real-time simulator is interfaced with the controller board, real controller board that is utilized as it would be used in a real application. So we are using all the peripherals, we are using the processor and so on. And consequently, this is called CHIL. CHIL stands for controller hardware in the loop. The real-time simulators are sending the analog signals to the controller. They are amplified with signal amplifiers, and the controller board is sending back the digital signals. And for that, we are using level shifters. So the interface board, essentially, for this approach, CHIL approach, is really simple. This environment, of course, allows us to do test automation. It's a versatile environment and so on. But as previous approaches, this one is also quite safe. There aren't any high power parts or equipment, so we can really do whatever we want without being afraid whether something is going to be destroyed or someone is going to be hurt. And now we have, of course, a similar approach. It's called power hardware in the loop. The difference is that here we are using a real piece of hardware, so it can be a real inverter, it can be some other power electronics device, which is of course advantage. If you want to really test that particular device, this is the way to go. Again, we are emulating some power stage with a real-time simulator, but the problem here is that we have to use really complicated interface boards. In this case, we really need to practically change the signals that are given by the real-time simulator or taken from the by the real-time simulator into the domain of real powers or real currents and voltages. And for that, we need an amplification. And this amplification, in comparison to a C-Hill approach, is really much more complicated. It introduces latency, and also it can cause even instability in such setups. So the topic of really interface boards is a topic of ongoing research. There are some solutions, of course, that can be found in literature, but it's not, easily solved. The problem of latency and stability is not really easily solved with this approach. Of course, we are talking about the real-time simulation here also, which is a great advantage. And now we are coming to something kind of more complicated, co-simulation approach. Co-simulation really means that we can, or our setup consists of several, perhaps even power hardware in the loop and controller hardware in the loop devices. Briefly, I won't go into many details regarding this approach. This approach essentially has the advantages and disadvantages of both of the two previous approaches, but it's quite expensive and it's quite complex and really hard to manage. Again, we can talk about this approach in more details afterwards if someone is interested, but it is not something that is relevant for local energy communities. Now, again, something that is really important for local energy communities is the co-simulation, let's call it version 2.1, in which case we are using several real-time simulators, so several emulators that are connected together, and we are using more than one, usually, controller boards. This approach, this co-simulation approach allows us to run in real time more complex models, right? So it's in a way a generalization of C-Hill approach. This is, of course, really convenient for local energy communities. And I should add that some vendors are providing the emulators in which the power stage can be included, but also pieces of code or pieces of some control schemes can be included. They can be simple. They can be regarding the coordination of the network or something like that, protection perhaps. But on the other hand, there are the vendors that are providing sufficiently powerful emulators that can run the power stage, but also complete control structures that would have been implemented in the controllers. So we have the power stage emulated and also control schemes emulated on the same platforms, which really, again, simplified the setups hardware-wise. And also there is one more thing that occurred essentially by introducing this approach is that now we don't really have any technical obstacles in running these models even faster than real time. So since the control code and power stage is implemented on the same platform, we can actually even make the emulation faster than real time. Not too much, but it can be maybe 1.5 or 2 times faster than real time execution. And now we are coming to something that is really really complicated. May I add, it's perhaps obvious. There is a way of using geographically dispersed setups together. They are interfaced, of course, through some particular communication network. And immediately, of course, we see that there is or there could be a problem of latency. This is also something that we can talk about later on. Perhaps it is not really a problem, but the question is why are we even using these kind of setups? There are a couple of reasons. One is that we can really share the resources, so someone can essentially sell a usage time of their resources and generate new revenue streams. Also, if we want to model really complicated systems, order of magnitude of whole countries or even continents, then a couple of research institutes can join the efforts and use not 10 emulators but 20 emulators to really execute those complex models. But perhaps the most interesting or most important aspect of this way of co-simulation is that we can really preserve the privacy, data privacy, because we can essentially allow third party to access our model without giving that third party the real data regarding that model. So if we want to test our inverter or whatever onto some network, and we have that network data, and of course the data regarding that network is sensitive, we don't want to share it, we can establish such a co-simulation setup and allow that vendor that is producing inverters to test it on our grid model. Of course, this is an interesting interesting approach and interesting way of doing digital twinning, but is really expensive and it is really complicated and complex, difficult to manage, and there is only a handful of those really worldwide. And now we are coming to what are we doing in creators. It's really actually simple if you understand what has been said previously. We can really use a real-time simulation together with controllers or without them, so C-Hill or just Hill emulation, but we are moving them behind the cloud. Okay, so we aren't really talking anymore about the emulators being on your desktop. We are talking about the emulators that are in the cloud. So why are we doing this? First of all, we want to streamline the implementation and parameterization of models. This is hopefully going to be done using our APIs. So the user is going to provide these the cloud service essentially with the topology of the network and the data regarding the setup itself. So what is the installed powers of certain asset and so on. And the models will be automatically or semi-automatically built, compiled and executed, and the user will then receive the emulation results. And also we want to essentially allow third-party services, again cloud services perhaps, to be utilized, and this is really in relation to what Igor has been talking about. And after me, Alexander will say a few words regarding those services also. Also, there is a small change or the kind of same thing, but the difference is that now we can also move offline simulators behind the cloud. So we don't really need to use the real-time simulators, but we can use offline simulation. The difference is, generally speaking, or to simplify, the first version using real-time simulation is when we want to execute real detailed models. So when we want to analyze voltage, transient voltage stability, or state voltage stability, frequency stability, and so on. But if we want to test some steady state or to make a steady state analysis, then we can use less detailed models, and they can be executed on offline simulators. And the really important thing is that these simulators are really, again, made for these kind of systems, and consequently they can execute the models quite oftentimes much faster than real time, as you will see in the following demo. Again, I mean, I wanted actually to show you the software itself, but for these hop-in reasons, I have decided to show you a video briefly, and so some things will be omitted from the discussion. But here you will essentially get the idea how our toolchain looks like and what is going to really happen in the cloud once our services are developed through the Creators project. So this is a model of our of one location in Spain of our partners from the consortium. Here you can see essentially a couple of passive nodes, and here we have a PV system, and also we have a CHP. What you have to do essentially to make this model at the moment is pick and place the elements from the library, make the network, and parameterize them, all the elements. So in case of PV system, you need to set what is the installed power, nominal active power, nominal voltage, nominal frequency. You should set what are grid codes that are going to be used, what are the characteristics of the filtering, DC, and some other things, DC link voltage, and so on. And you also have to set the relevant parameters of the passive node. So installed power, installed reactive and active power. So some usual things, let's say, that are necessary for modeling such systems. And then, once you finish making the model, you run them or compile them, and afterwards you will be able to run what is called HIL-SCADA, in which we are able to gather all the necessary information that is going to happen. So it looks like this, essentially. And bear in mind, here we have 2 minutes of the simulation. So this simulation is made for 1 year of the simulation. And here, once this icon is pressed, you will see the zeros, because none of the months have been finished. But you can see what is happening during the day. During the day, the PV system is producing some power. During the night, it's not producing anything. Essentially, here on the left, you can see cumulative active power. And here we are going to have the data for the PV system itself, 1 day, 7 days production, and we can set the temperature, reactive power production, and so on. Whatever we can actually set in a real life application. This is the active power consumption, reactive power consumption, again, all the zeros per month. This is the start of the simulation. Now, 6 months later, which is really some 30 minutes of the simulation. So roughly speaking, we need 1 hour for 1 year of simulation. We can see that, for example, I mean, the April was pretty sunny month, since the consumption was the smallest. We can see again what is happening on the day of level of 1 day and so on. The goal of this simulation was to find out whether we are going to have congestion problems within the said network. And as it turned out, there was no problems. But what I can't show you right now is that exactly the same looking model could be made. It would consist of again same looking elements, but they would be modeled with a little bit more detail. The power stages would be modeled with a little bit more detail, and that model could be used to make some tests that are considering higher dynamics, essentially. And of course, that model would be run much slower, but still at least real-time simulation could be achieved. And also, the models themselves can be run on, I'll quickly finish.
If you can get finished, so we have time for Alexander's presentation.
In maybe 2 minutes or less. So all the models can be executed on the emulators on the PC, personal PC, and of course in the cloud. So to conclude, there are many different ways how we can conduct our digital twinning. Some of them really are not meaningful for local energy communities. Controller model really isn't something that we are interested in, but even those that are regarding the power hardware in the loop aren't also something that we are supposed to consider that much. But what we are using and can use, it's a model in the loop, software in the loop, C-HIL, so controller hardware in the loop, cost simulation, and of course we are developing at the moment cloud services that are going to enable us to essentially do what we actually want to do. We are wanting here to essentially become Laplace's demons, which really means that we really want to know what is going to happen with our local energy communities, and not just assume something and wait for a year or two for the essentially information loop to close. So yeah, thank you very much.
Thank you very much, Ivan, for your presentation. It was very interesting, especially to see the simulation. Thank you very much. And now I'm going to leave the floor to our last speaker, Alexander. Please, Alexander, keep in mind the time, 15 minutes, because there's another workshop starting at 5:30, please.
Yes, thank you. I will try to be as quick as possible. So let me just share my screen. And I will actually turn on my stopwatch to make sure I follow the right time. So just confirm, Blanca, if you can see my slides and everybody else.
Yes, we can see them.
Okay, great. So
once more, just like many other people, I'm really happy that we managed to organize this workshop. Thank you to R2M and Blanca, and thank you to Cordial, AECOO, and of course COMSA, Turbulent, and everybody else who contributed to these slides. And it's a shame that I also couldn't be in Rome, because all roads lead there, but hopefully next year. Very briefly, so as you heard, these tools that we have from AECOO and Typhoon will be integrated into a cloud platform that we call Simulation Emulation Engine, SEE. And the reason, we are doing this, as you heard, primarily the efforts are led by AECOO, but also 50%, let's say more and more equally by Typhoon Hill. But we should not forget the company that was mentioned several times, Turbulent, the producers of these turbines for tidal energy plant and hydro, and of course the Jožef Stefan Institute, and as Boris mentioned, we are working closely because Jožef Stefan Institute has a great expertise in, for example, modeling of waste heat. So this will be integrated into this platform. So you already heard the description of Typhoon, so I will just mention that we are present in industrial sector. These are some of our industrial customers. Usually these are OEMs like ABB, Schneider, Toshiba, Caterpillar, and General Electric, etc., Fronius. And we also have a lot of traction in academia, but I will skip this part. So the main question is why we are integrating these tools. Why are we creating the simulation emulation engine? Primarily because of the things that Energy Pro, maybe I'm using the old name of the company, and Bex told you about when you approach people who desperately actually need a local energy community, there can be some doubtfulness, some, let's say, puzzlement and unclarity, because this is a new technology that is actually now being implemented by innovators. And very partially, these early adopters, you are probably familiar with Crossing the Chasm by Jeffrey Moore as a paradigm. So the people need to be sure that they can enjoy a complete peace of mind when this is deployed into their physical sites, that there will be no negative effects, that actually all the positives that we are bringing financially and in other respects are also going to be followed by stability in the technology that makes it happen. And this is actually the idea of the simulation emulation engine, to actually create a platform that can be used to assess the capabilities for a particular local energy community, and in the process show stakeholders, decision makers, that we can that this is actually devoid of any significant risk. So this is what we are creating. So you already saw the screenshot and the video by my colleagues, Ivana and Ivan, although Ivan was presenting, but it was their joint effort. So this is a model of Castilla y León, one of the tier 2 sites. So in the project, we are creating digital twin and models of tier 1 and tier 2 sites. This is a big picture. There are many levels below this, but ultimately, the simulation emulation engine will enable you to create this kind of schematic for your local energy community. Behind each of these boxes is actually a separate, let's say, facility. Specify its power, specify, for example, the capacities of the batteries that are present there, specify the mode in which a specific part of the site or a device operates, specify the type of the grid that you're emulating, stiff or weak grid, and then choose a scenario, whether it's kilowatt max, time of use, self-consumption, and then simply run this model based on these parameters, taking into consideration that you don't have to use any specific tools, but can access this from a browser window, where data for this scenario comes from AECOO database, or theoretically there would be maybe even a possibility to upload some comma-separated values. Or in case of partners in the project, this will be also coming from real gateways, so you could do A and B testing, and you can then visualize this scenario in the AECOO cloud. And AECOO, in addition to everything that you heard from Igor, is also an expert in creating wonderful visualizations for different scenarios, including, you know, the energy you spent, you saved, the profit you're making, but also the details on each of these scenarios. So that's the ultimate plan, to have a platform that allows you to see. That's why we call it SEE, Simulation Emulation Engine. It allows you to see the big picture of the local energy community that you want to build. And in this respect, we are actually following, because there's one part missing that I couldn't include properly in this animation, we are including some additional capabilities that actually make this simulation emulation engine similar or actually compatible with the paradigm that you know from you know, maybe other projects, or from general, you know, system engineering. So that's the famous V model of system engineering, where you start with requirements, functional specification, high-level design, detailed design, then you code, develop, and then test units, then test integration, the system, and ultimately going through unit, integrated, and system test plans, you reach customer satisfaction and successful commissioning. So with AECOO and Typhoon, Jožef Stefan Institute, and Turbulent, we actually can apply this paradigm of going through verification, build, and validation to local energy communities. So the first part will be, of course, local energy community requirements and their functional specification, followed by techno-economic analysis, detailed simulation, development of specific optimization for the given local energy community. You know the big joke about local energy community. If you've seen one local energy community, you've seen one local energy community. Every single one is different. There's no one size fits all. So once you do those optimizations, you test whether you can control and optimize individual devices. Then you make sure that integration works, the system works, and you get acceptance ultimately again through these cycles. And in our consortium, we are very fortunate that we have partners, for example, Turbulent, who's leading efforts. This is from work package in our project that is about plugins for the renewable potential. So we will be able to assess for a local energy community in the particular geographical location whether which mix of solar, hydro, or wind distributed energy resources is the correct one. This part of the V-curve is covered by AECOO, and of course Typhoon Hill is in charge of digital twinning, which are used to validate all the optimizations in the minute details. And the project itself is this state-of-the-art where we get successful commissioning. On top of that, this paradigm, which is based on cooperation with our wonderful partners, is that the platform can also be used beyond the project for the complete life cycle, because once you have these models in the simulation emulation environment, you can test the model, you can keep the model as a digital shadow of your real site and try to see how it matches upcoming or new grid codes. You can use it to assess the validity of new business models, test how new assets could benefit or be detrimental to your local energy community, and generally analyze new optimization. So we see this SEE, no pun intended, we see SEE as life cycle management tool for local energy communities. Of course, we are now halfway to making it happen. We are in the development phases, but we are already ensuring integration, and the models and the optimizations are being developed, as you heard from AECOO, and as also you heard from our AECOO partners in Cordeal and COMSA and everybody else who presented. So since time is running out, I will skip the minute technical details. I have many slides, but fundamentally we use the know-how from a previous project where we had successful cooperation with AECOO, where we were focused on 5 pilot sites ranging from industrial to residential, where we were focused on simply demand response in the sense of switching on and off and shifting loads. And we are now and this is the user interface required a degree in coding. So we are trying to abstract this knowledge and make it possible for decision makers, stakeholders to run these emulations and simulations to actually assess and see for themselves the benefits that local energy communities can bring to their communities. So this is the detailed schematic, but we don't have time for the details. Very simply saying, AECOO will enable data streaming to the digital twin, because the digital twin will have to know with what parameters to start, what's the state of charge, for example, of a battery, what's the mode of operation of solar inverters. And in order to actually test this safely, the cloud controlled by AECOO has to be sandboxed. So there will be, let's call there will be a sandbox environment identical to the production, where instead of controlling real assets, you will be controlling digital twins. And of course, for each scenario, we will define KPIs. From Typhoon Hill, as you heard, we are fundamentally focused on Hill emulators as a hardware. So we will have to first enable access. I really apologize for this. And we will also have to enable cloud-based interaction with digital twins, loading them with historical data and live data as well. But fundamentally, since we don't have time, I will skip to the penultimate slides if my PowerPoint decides not to crash. So we will achieve, knock wood, complete de-risking of lag creation, because you will be able to explore what-if scenarios with historical data. You will be able to benchmark optimizations in parallel to the real site. So with the digital twin, you can say, oh, right now, what if I actually applied a different optimization? And you will be able to do that. And since we all digital twins actually use the same Modbus and similar registers as the real devices, you can do pre-integration, leading to shorter commissioning. And from the point of view of stakeholders, you can use these simulation and test runs to actually show various revenue stream, assess new revenue stream. And as I mentioned, with the digital shadow, if you keep this running after you've commissioned the local energy community, you can support the life cycle. So this is the story of the simulation emulation engine and why we are integrating our tool chains. We want to see the big picture, but we also want to see the details, because you need the big picture, but you also know that the devil is in the details. This actually is the devil is in the details but from a bird's eye perspective. So thank you, and Blanca, I hope I managed to squeeze into 15 minutes.
Yeah, you actually did, Alexander. Thank you very much. It's highly appreciated. I would like to thank all the participants on the event, both virtual and in-person participants, for collaborating and for your efforts so we could do this event and disseminate about our project creators and about the community energy systems. I hope for the virtual and in-person attendees you were able to understand what creators is about and especially the work we are trying to do. So thank you very much, all of you. And I hope next year we can do the conference at all in person in whatever location it takes. So thank you very much.
Thank you.
Thank you.
Bye.
Bye-bye.
Bye-bye.